Good evening, good morning, from whichever part of the world you are. I'm very pleased to announce that this is our 50th webinar, and we have with ourselves Dr. Rakesh Kumar Khali. He is a highly distinguished tunneling and underground works expert with over 3 decades of experience and extensively in Himalayan geology. He holds a Bachelor of Engineering in Civil Engineering, Tech in Tunnel Engineering, MBA in Project Management and Construction, and Safety Management, and also has been awarded an honorary doctorate in recognition of his outstanding contribution to the field. Currently, he serves as Vice President Operations at GR Infraprojects Limited. There, Dr. Khali leads strategic and technical operations across tunneling, underground infrastructure, and hydropower projects. With over 30 years of experience, his career spans leadership roles in premier construction organization, where he has spearheaded numerous complex and large-scale underground works in challenging geologies. Dr. Khali is also a prolific contributor to industry knowledge, having authored over 100 technical papers in national and international journals and conferences. Uh, he's a global authority and a proud recipient of ITA Fellow Award and multiple prestigious national awards, including Golden Achievers Award, Pride of India Award, Hall of Fame Award, Glory of India, Indira Gandhi, uh, Somani Award, Bharat Jyoti Award, and International Professional of the Year Award. He has also represented India as an official voting member of TAI at numerous ITA World Tunnel Congress. Dr. Khali is also an esteemed member of ITA Working Group 5, serving as an official representative of TI. We are pleased to have you, sir, on our platform. Over to you, sir. You can start the webinar.
Thank you, Lucy, for a nice introduction. I welcome all of you in this evening, and I'll try to make it interesting. Hope you all will like it. So I'm presenting this webinar on geological complexities in tunneling, management approaches, and safety practices. So I have selected three projects which I have recently completed. One is Tista 5 hydroelectric project, 510 megawatt. Then TAIym pump storage project, one of the prestigious pump storage project in India. And the other one is Vishnugad People Koti hydroelectric project. So I'll brief the details of these projects in the subsequent slides. So I'll first go to the next slide. This flow of my presentation will be like this. I'll give an introduction of these projects, overview of the projects, challenges in working with Himalayan geology, challenges in working with Himalayan geology project specific, mitigation strategies for geological challenges project specific, importance of excavation sequence, blasting techniques, excavation methodology, blast design, support system, importance of instrumentation and monitoring, future scope in India, safety measures, underground safety do's and don'ts. So this will be covered in my other slides. So I'll go to the introduction now. So these hydroelectric power projects such as People Koti hydroelectric project, that is 444 megawatt, is under construction in the advanced stage. TAIym pump storage project recently completed. Two of its turbine, 250 megawatt each, has been commissioned, and balance two are in progress. In next 3 months, that those three will also be commissioned. Those two will also be commissioned. And Tista 5 involve extensive underground works, including headrace tunnel, tailrace tunnel, access adits, large underground caverns. These structures are interconnected. Tunnels provide the primary approach and water conveyance routes, while caverns house turbines, generators, and auxiliary systems. So this we will discuss further. Each project faces distinct geological complexities, from intricate rock mass condition at Tiri to high seismicity at Tista 5, which comes in Zone 5. We consider the seismology, which directly influence the excavation design, sequencing, and support system for both tunnel and caverns. Effective tunneling strategies combine excavation, precision, controlled blasting, robust support installation to ensure structural stability, worker safety, and long-term performance of underground infrastructure. So, overview of the project TDPSP. First, I'll talk about this project. The highly very important project. It is under construction. Now it is almost complete. 99% has been completed. It is located in the same hillock that house the operation of Tiri hydropower project. It features a vast underground machine hall caverns designed to accommodate four reversible pump turbines units of 250 megawatt each. So key underground works: machine hall that is 26.2 meter wide, 57.3 meter its depth, and 203 meter approximate in the length. So four turbines are there, 250 megawatt each, and diameter of each turbine is 22 meter. So surge arrangements: two upstream surge set with chambers, two downstream surge set chambers, 18 meter dia auxiliary caverns, butterfly wall chamber (BVC), and PAC. These are around 70 to 80 meter in length, 20 meter in width, and 13 meter in the height. We have to come down. And tailrace tunnel. Two twin tunnels were there, 1081 meter and 1176 meter, that is in highly adverse geological conditions. So you can see this view of these uh, this layout of this project. This it looks very complex, but I'll show you the uh, prospective view of this so that you can understand each and every part of this. Proximity blasting operation optimized considering proximity to the operational Tiri hydropower project powerhouse, because it was a running project. Total Tiri scheme is meant for 2400 megawatt. 1000 megawatt is the hydropower project. Then 22-kilometer downstream, there is one more project that is called Koteswar Hydroelectric Project. And third stage, it comes to Tiri Pump Storage Project, which we are discussing now. And that reservoir of that Koteswar project is ending at the TRTs of this TRT outfall of this project. And then we are using this reservoir for reversible turbine to during lean period. So this is the last stage. 1400 is already commissioned. Now 1000 megawatt is to be added in this. So two turbines already commissioned. So I'll go to the next slide. This will give you a clear idea of this project. Just see the network of tunnels here. First, you can see upstream Sursat 3, upstream Sursat 4. There is one access added to reach to the chambers. And we have to make a cavern and then start these 140-meter deep sursets, butterfly wall chamber, penstock assembly chamber, drainage gallery around the surset, vertical penstock, vertical tunnels, draft tube, machine hall, bus bar, TRT 3, TRT 4, downstream surset 3, downstream surset 4, and TRT outlet structures that is also there. So all these things are here, you can see visible here. So aggregating length of this network of tunnel is 20 kilometer. So there are number of tunnels. It's a mess. It's like a bhul bhulaiya here in Indian typical language. So if you don't mark the area, you cannot reach the real location. You have to, it will take another 1 month to understand everything, where to go, where not to go. So it's a very complex structure and very successfully executed by our team. Now, hello. Yeah. Hello. Yeah. Yeah, it's moving now. Okay. Overview of the project theory pump storage, cross section of the caverns and layout. This is the first one, is the section for powerhouse, where upper arch, and then we have to go down to 57.4 meter, and the last one is the draft tube. So sequential excavation, first we constructed this arch here, and then stage wise we have started doing it, and finally we could complete it. And then every blast 1.5 meter we have taken, and we have gone down to this place. Then we executed this very successfully. First stage, there were some edits, then horizontal penstock location, and then there were access to reach here, and then final excavation was done through these draft tubes. These are the butterfly wall chamber and penstock assembly chamber. Just see, first we made the cavern and then we brought it down. And after coming 3 meter down here, then we started the penstock assembly chamber here. And we came it, there was this distance was around 17 meter. So there was no possibility of making any changes in this. We have to go as per geology. Geology was very weak. So initially, a lot of stress we have observed. They, our design team has provided this 12-meter long rock bolts, but we have seen a lot of stresses here. So knowing the fact that stresses are developing, we have taken a call based on the instrumentation reading, and we started doing the cable anchors in this wall and through anchors, inclined anchors. Finally, we could restore this wall very successfully, and we could complete this BBC and butterfly wall chamber very successfully. This is the plan which we have already executed. All green things are there. So there is no problem. We can, now it's all the part of that commissioned project. Now I'll come to the Peoplegoti hydroelectric project. That is 444 megawatt project. This it is in advanced stage of construction by TSDC. It's a run of the river hydroelectric project located on the Alaknanda River in Chamoli district of Uttarakhand. The project is designed to generate 444 megawatt of electricity, addressing the increasing energy demand in northern India. Location between Hart village and People Koti in Himalayan foothills. And from the dam side to powerhouse, it is around 52 kilometer you have to uh, travel. And major components of the projects are divergent dam, 65-meter high to 34-meter long, and 2.8 million cubic meter reservoir. Headrest tunnel 13.4 kilometer long, 8 meter in diameter. Out of this 13.4, 1.4 kilometer we have done through NATM, and balance 12 kilometer we have bored it through 9.86 meter dia TBM, double seal TBM of Terratech. Sursaft 15-meter dia, 145-meter high, that is also boring is complete now. And butterfly wall chamber is also there for 50 by 11.5 by 26 meter. Penstock assembly chamber is also equally same. Underground powerhouse 411 megawatt Francis turbines, 134 meter by 22 meter by 49 meter caverns. Underground transformer hall 142 by 16 by 25. Downstream surge tank 150 by 16 by 34. And tail race tunnel 3.07 kilometer long, 7.5 meter dia. Every structure excavation is now complete, and somewhere we have started lining also. So this is the dam complex 3D view. There are three desilting chambers that is also complete, and concrete lining is also complete here. And dam foundation concrete is already started. Divergent tunnel already uh, commissioned, and we have diverted the river through this and to facilitate this construction of dam. So this is the 3D view of powerhouse complex. You can see all three chambers: butterfly wall chamber, penstock assembly chamber, and powerhouse cavern, transformer cavern, and all this. Sursaft also you can see here, 140-meter deep. There is two sizes. And now I'll come to the Tista 5, where we have constructed 17-kilometer long tunnel. Tista Stage 5 hydroelectric project is a significant infrastructure development situated in Tista River in the Indian state of Sikkim. It is a key part of series of hydroelectric project planned on the Tista River to harness hydroelectric power potential, developed and operated by NHPC Limited, that is National Hydroelectric Power Corporation. And project is a major contributor to the renewable energy sector in the region. It's in East District of Sikkim, near Dikchu and Singtam. Installed capacity is 510 megawatt, three turbines of 170 megawatt already commissioned. Major component of the project: dam, concrete gravity dam 95-meter high, 180-meter long, designed for high seismic activity. Headrest tunnel 17.69 kilometer, 9.5-meter diameter, that is finished diameter, and excavated diameter is 10.5. So we use heading and benching for this. Sursafe 25-meter dia, 92-meter high. Underground powerhouse cavern 100 by 22 by 49. And head between the powerhouse and dam is 240 meter. Tail race tunnel 135-meter long, 6-meter diameter, and surface switchyard is 110 by 60. Steps up power for 400 kV. So overview of the project, it is like this. It has to be operated this 17.69 kilometer tunnel from 10 phases through 5 edits. And the project starts from Dikchu and ends at Singbel near Singtam. There are 5 edits. and maximum rock cover was 800 meter and minimum was 88 meter. So we have bored this tunnel through varied geology, very poor geology, and we face 18 cavities during operation. And I'll come in the next slides. We will discuss the geology also and how we have mitigated the geological problems which we faced. So challenges in working with Himalayan geologies. Seismic activity, the Himalayan rank among the most seismically active regions globally due to the ongoing collision of Indian and Eurasian plates. Frequent earthquakes can affect the stability of underground excavation. Designing large caverns and tunnels in such environment demands construction of seismic loading, consideration of seismic loading, robust support system with withstand potential ground shaking, complex geological structures, folded and fault rock masses, intense tectonics produce tightly folded strata, multiple faults and shear zones, creating unpredictable ground condition. Fault zones act as weakness, increasing collapse or deformations risk. Heterogeneous rock mass, variable degrees of weathering, fracturing, and joining mean different sections respond differently under stress, complicating stability control. High in situ stresses, significant tectonic stresses can cause rock burst, spalling, and other stresses, including damage during excavation. Large cavern stress redistribution, effective management requires careful excavation sequencing, appropriately designed support system, water ingress, water bearing strata, especially in fractured fault zones, can cause heavy groundwater inflow. Challenges include dewatering requirements, waterproofing measures, and mitigation of instability due to water pressure. So challenges in working in Himalayan geology, project specific, I'll now talk with this TISTA 5 project. Diverse rock formation, unpredictable conditions make excavation challenging. Fault and shear zones increase the risk of instability, extensive support system needed, elevated stress levels, risk of rock burst, careful stress management requires stress redistribution, ongoing adjustment necessary to maintain stability, high groundwater pressure, significant flooding risk, advanced dewatering techniques needed, fracture relation, uh, fractures related seepage, managing water ingress to maintain dry working conditions, seismic activity potential for induced seismic effect affecting excavation stability, support design, robust design required to handle seismic impacts. These problems we faced in Tista 5. We will discuss some of the cases which we faced and we rectified. And now I'll come to TAIym pump storage project, highly folded rock strata, unpredictable rock formations and complicate excavation, presence of faults and shear zones, increased risk of stability, extensive support system required, high vertical and horizontal stresses, risk of rock burst and collapse, stress redistribution, continuous monitoring to manage stress challenges, high groundwater pressure, risk of flooding, advanced dewatering needed, seepage through fractures, challenges maintaining dry condition, tectonic movement, potential for Induced seismicity impacting structural integrity, robust design requirements, cavern support system designed to withstand seismic forces. People Koti HEP, now I'll come to this. Varied rock types, difficulties in excavation due to unpredictable rock condition, presence of fault zones, increased instability, need for reinforcement support, significant stress variation, risk of rock instability requires careful monitoring and management, stress management, and regular adjustment needed for safe excavation. High ground levels, risk of flooding, efficient dewatering system is crucial. Fracture associated seepage, ensuring effective control over water ingress. Active tectonic regions, potential for earthquake affecting excavation stability. Design consideration, enhanced support and safety measures required. So this is the real-time geological challenges as this the five we faced. Now I'll come to the first picture. While doing at phase two, while doing the benching, 16 rib collapsed because of because we have done the entire thing. We have gone in class 4 and class 5, and due to the slight mistake of our subcontractor, he has done scoring there. He has taken a big blast there, and then whole 16 ribs collapse at a time, and it took uh, 3 months to stabilize this area. We have packed the face and then rectified the ribs, and then segmental arch erection we have done. We have done the concreting above this after packing the face, and then finally restored this area. The second one, the second picture shows, here you can see the vertical horizontal thrust is coming from the right side, and you can see the drift here and vertical props. See, in this area, there was a perennial source of Rangchang Khola on top. So entire water of that stream came inside. It was a huge water and there was no flow on top. Entire Nala got diverted in the inside the tunnel, and that was a real challenge faced by our team. And it took more than 1 year to establish this area, and whole project got stuck up because of this cavity at phase 4. So we have done a lot of efforts to channelize this, and we used MG10 pump and Maheshwari pump for this doing the grouting, and we placed the dry mortar on the ground. Then with doing multi-drifting and segmental arch erection, finally half of the portion we have opened, then balance half also. After making a road to pass through, and then from the back end, we have taken care and channelized water at one point. And finally, we succeeded and cleared this cavity. And then third one, it is near phase 5. You can see the buckling in crown. A lot of cavities were there. And then this size got squeezed. Then finally, with providing this vertical prop and multi-drifting, we could restore this also. And here also you see the buckling in the verticals below the arches. And here you can see this face was packed, then multi-drifting operation is going on. Here you can see the cavity on top, and then with 4 pulling and other thing we have done it. And the other one is also one more cavity at 966 level. from this phase 4. This was also very critical, but finally lot of water seepage was there, and finally we restored it. And the other one, you can see we have done the lining up to this, and extreme end, the whole face got collapsed. Stresses were developing, and this also we could rectify uh, with innovative techniques. The mitigation strategies for geological challenges, seismic hazards assessment, detailed seismic studies conducted to understand fault zones and potential seismic impact, design adaptation, structural design tailored to withstand seismic forces, including reinforced concrete lining and flexible joint system wherever is required, rock reinforcement installation of additional rock bolts and anchors in fractured zone, grouting at fractures, injection of grout into rock fractures to fill the voids and improve rock mass stability, seismic monitoring, installation of seismic sensors to monitor real-time seismic activity and vibrations, adaptive blasting techniques, modification of blasting sequence in minimize seismic impact and protect surrounding structures. Now, real-time geological challenges which we faced at TAIym Pumped Storage Project, because we were constructing this project at one hillock, so there was no possibility to do any rerouting, any change, any mitigation on this. We have to construct in that geology. People were saying that it is not possible to construct these big caverns, butterfly wall chamber and penstock assembly chamber, because rock geology was very bad. And these were connected through a 17-meter long, 17-meter wide wall. And initially in design, they provided rock anchors of 8 to 10 meters, rock bolts. But when we see, we have done monitoring, we have placed the monitoring instruments here, but a lot of stresses were developing and a lot of pressure were coming. So finally, we changed that. We have installed 400 cable anchors, through anchors, vertical anchors, inclined anchors with the consent of our client. And finally, we restored this wall. You can see here. Just see how many, lot of rock bolting is done in the crown arch. Here also you can see, even though they have done the SFRS after placing the ribs, nowhere we have seen, but our client insisted and we have done it. You can see this wall, which we protected with the help of placing cable anchors here. Both sides we placed 400 anchors here. And finally, this project got commissioned. And with our innovative and progressive techniques and support of our client, we could succeed in this. Cavity formation at TRT, you can see here a lot of challenges. 18-meter cavity formed, and finally we restored it. We placed the pipe here to fill this cavity, and uh, in this powerhouse top arch excavation, you can see a lot of challenges are there, lot of overbreak we have observed, but we used steel fiber reinforced concrete and that worked very well. And finally, we could match the timeline also and successfully completed this cavern. So mitigation measures for geological challenges, grouting techniques, extensive pre-excavation grouting to reduce water inflow, post-excavation grouting to seal the leaks and stabilize rock mass, drainage system, installation of robust drainage system along the 57-meter long umbrella holes to channel water away from the critical area, So there were inspection galleries built along the powerhouse, around the powerhouse, and our client they suggested to do the 57-meter hole, umbrella holes from the both the using those drainage galleries. It was a big task how to drill that hole. Then we have done some innovation. We placed uh, a ROC on a tractor, small tractor, and finally we could do 57-meter hole and 140 numbers of hole we have drilled in this. And out of this 140, drilling up to 138 numbers of holes, we could not get any water. But finally, in 139th hole, lot of water came from somewhere, and the ground got stabilized, and the whole uh, this drainage gallery was submerged with water. And finally, our structure got safe because we have taken out the water on the ground and we could succeed in this. And that was the turning point of this project. Systematic rock bolting, rock bolts installed systematically to reinforce the rock mass. Steel fiber reinforced short kitting. Application of SFRS was very successful to these cavern walls. Additional support and to prevent rock falls. Cable anchors, use of long cable anchors with anchorage to secure unstable rock masses in between nearby structures and in areas of high overburden pressure. Instrumentation and monitoring, continuous monitoring of rock movement and deformations using sensors like optical reflectors, multi-point borehole extensometer MPBX, load cells, etc. Adaptive excavation, adjustment of excavation method based on the monitoring data received. And we have revised our design based on these monitoring interpretation. And finally, we could succeed because we were not having any option to change any alignment, anything. So you can see the challenges at People Koti project. First, where we were using the TBM edit while going around 7 meter, 7 to 10 meter, we faced a lot of problem. We have taken the TBM inside in a TBM edit we constructed. Then after moving 7 meter, we found more than 1 cubic meter size of boulders there. It was a river basin in the past, and we faced a lot of problem. 200-meter stretch was very critical. Then we have made a additional bypass edit and from the bottom and horizontal edit to reach to the front because our TBM got stuck up and it took more than 1 year to take out the TBM. And finally, we reached in the front, we made the cavern there, and then we have pushed the TBM up to 200 meter. Now it is working very nicely. We have achieved more than 600-meter progress in a month. And out of this, 9 kilometer tunneling has been done successfully so far. And in next 3-4 months, we will be completing this tunnel through TBM. This is the largest dia TBM used in Himalayan geology, that is 9.86 meter. The other one also for this, we have used the vertical props to stabilize that edit of TBM. And the third one here, you can see this is the powerhouse cavern. You can see there is more than 24 meter, this machine hall. And after reaching more than 100 meter, there was a collapse and we have faced a cavity above the ground more than 17 meter. So it took 6 months to restore that cavity in the stretch of 20 meter. And one by one, we have erected the rib, and then above this ground, 17 meter. So lightweight concreting we have used here in the ground, and finally successfully we could complete it. And then we have gone down and we used the cable anchors here and successfully completed this powerhouse cavern. Now concreting is going on. This is the transformer cavern. This is also very big structure. This is the central gullet we have completed, but here also we faced uh, one or two cavities, and that has also been restored in similar manner and successfully completed. In HRT phase 1, it got open to the sky at a low cover zone. Then we rerouted it in TAIym area, and finally this also we have restored. These are the common geological problems, but here we have used the monitoring system and data interpretation. We kept uh, our instrumentation people. They have kept a specialized engineer at site who used to take the reading with our surveyor, and interpretation used to come every week. And then we used to provide it to the design team, and finally we are making the changes as and when required. So you can see this other one, heavy rib support, you can see support system. And here also, this also we have mitigated successfully. And finally, project is coming in shape. It is in advanced stage of construction. So Vishnugad people coating mitigation strategies for geological challenges. Geological mapping, detailed geological mapping conducted before and during tunneling to identify weak zones and unexpected geological conditions. Very competent geologist has been placed at site. A geology team and design coordinator was there. Pilot tunnels, use of pilot tunnels to explore and assess the rock condition ahead of main excavation, sequential excavation method, implementation of SEM and manage rock loads, ensure stability during excavation, advanced rock supports, deployment of advanced rock support system like cable anchors, steel fiber reinforced circuit for the area with poor rock quality, geotechnical monitoring, continuous monitoring of rock deformation and stress using sensors enabled in the rock mass, sensor embedded in the rock mass, flexible planning, adjusting excavation sequence and support installation based on the real-time monitoring data. So this way we could mitigate this. An entire team was aligned. We used to keep, before going to site, we used to do the meeting so that everybody is in the same wavelength and there should not be any confusion about the methodology to be adopted. So importance of excavation sequence. From this slide onwards, we focus on large underground caverns, which due to their complexities in geologically and challenging terrain require careful planning and specialized execution. Excavation sequence refers to the planned order in which rock mass is removed during sequential excavation of the caverns. The methodology to be adopted for sequential excavation is planned based on the various factors such as the dimension, depth of the cavity, of the caverns, specialized machinery to be deployed, availability of access edits for muck removal, geology and contractual conditions. So importance of the proper sequencing in hydropower projects, stability of the rock mass. Underground tunnels and caverns in hydroelectric projects are excavated within the rock masses. Already under significant natural stress, poor sequencing can trigger destabilization, causing cracks, fractures, or even collapse. A well-planned sequence preserves rock mass integrity, reducing the risk of geological failures, minimizing ground movement. Uncontrolled excavation can cause excessive ground displacement, affecting tunnel alignment and structural integrity. Proper sequencing enables controlled excavation, minimizing deformation and ensuring stability of both underground structures and surrounding slopes. Now, the important thing ensuring the safety, sequential excavation minimizes hazards such as rock falls, face collapse, and overbreak, enables timely installation of support system to protect workers and equipment, allow proactive hazards management by anticipating geological risks before they come they become critical. So blasting techniques, we have to use the controlled blasting because in theory, nearby structures, operational structures were there, projects were running, projects are there. A techniques where um, small, carefully timed blasts are used to control the fragmentation and minimize the impact on surrounding rocks. And the importance reduces damage to the surrounding rock, ensuring the integrity of the cavern walls. Pre-splitting and smooth blasting. Pre-splitting creating controlled cracks along the defined line to prevent overbreak. Smooth blasting, a method of blasting that minimizes roughness and over excavation, ideal for final wall cut application used effectively in Tista 5 to address the high seismicity of area. Vibration control techniques, use of delay detonators, reduce charge for delay, and blast design to limit vibrations. Application specific measures taken to protect nearby structure from the blast induced vibrations. So excavation methodology. The excavation of the large underground caverns are planned along with the construction of pilot tunnel, center gullet at the caverns summit, as well as side cutting in various phases of benching. Tunneling procedures were intended as the top heading together with the pilot tunnel. This allowed the simple access to the cavern roof for the installation of the support work. The supporting roof provided safe working conditions for the excavation of the cavern's lowest floors. Benching procedures were used to excavate the lowest level. Many concomitant elements were considered when determining the size of the top heading, which was divided into three portions, including the pilot tunnel, left side and right side slashing. These are top level sections were chosen based on the following criteria: drilling equipment reach, rock quality, the presence of weak rock zones that due to instability limits the area unsupported excavation phase, the amount of explosive release in one round is limited by blast vibration acceptance standards, the practical depth of the blast holes, which ranges between 3 to 4 meter, depending on the cross-sectional area of the top heading. So, excavation methodology for large underground caverns. You can see the pictures here, excavation sequence on top heading, right side, left side, slashing and cavern benching. Just see in these two pictures. Right side drilling, first we move in the gullet, and then from the right side slashing and then left side slashing by making the space here. And this way we proceeded. The height of the benches is decided based on the following factors. Tunnel placed at approaches level provide access and mucking. The longer the hole, the higher the possibility of deviation. If the cavern wall is too high, it may become unstable, necessitating the further bench excavation and support. Construction at a low cost with excavation cycle optimized. Restriction on the amount of explosive fired in a round as specified in the blast vibration acceptability criteria. So we have taken a pull in the arch portion around 3 to 3.5 meter, and while doing the benching we kept it 1.5 meter to 2 meter, and that way we proceeded, and accordingly we have make access road to take out the mud. Here this blast design. So in one of the if we were doing in one cycle of this uh, powerhouse, 24-meter wide powerhouse. So in one cycle, 101 holes we were drilling. That is 2 to 3 meter, and drilling length was around 303 meter, and explosive consumption was coming 118.17 per cubic meter. Support system. The stability of powerhouse caverns is critical in hydropower project, ensuring the safety and integrity of the infrastructure housing key equipments like turbines and generators. The support system for these caverns are designed to manage geological stresses, prevent collapse, and ensure long-term stability. At People Koti project, rock bolting, high tensile rock bolts were used systematically installed in the rain to reinforce the cavern walls and roof, ensuring they remained stable during and after excavation. Shortkit and wire mesh application. Shortkit along with the wire mesh was applied immediately after the excavation stage to prevent the rock falls and surface degradation, offering both temporary and permanent supports. At TD rock bolts employed at varied lengths is from 6 meter to 12 meter to manage the complex stresses within the cavern due to its large size and high seismicity of the region. Steel fiber reinforced concrete used extensively to enhance the mechanical properties of the shortkit layer, providing increased strength and ductility, crucial for withstanding the seismic event, and it proved uh, very well in this project, and we didn't face any problem after doing this shortkit, steel fiber shortkitting here. Long cable anchors, these were utilized to stabilize the deeper rock layers, particularly in areas with high stress concentrations, ensuring that cavern walls remained intact even after seismic loading. ISTA 5 seismic resistant bolting, especially designed rock bolts were installed to ensure high seismic loads, ensuring that the cavern structure remained stable during the seismic event. Double layer shortkit, two layer approaches are implemented, with the first layer providing immediate support and the second layer enhancing long-term stability and resistance to the seismic phases. Cable bolts and rock anchors, deep cable bolts and anchors were used in area with significant overburdens pressures, providing additional anchorage and preventing large-scale rock movements. So importance of instrumentation and monitoring, because this is nowadays very important. If we get the monitoring data and we are getting any stresses, stresses are developing in between, so we can revise our drawing design and timely to avoid any collapse. Instrumentation and monitoring are critical component in ensuring safety and stability of large underground cavern during and after construction. For hydroelectric project like Pipalkoti, Tihri, Tista 5, this system help detect potential issues early and guide necessary adjustment in construction practices. Pipalkoti hydroelectric project, geotechnical monitoring by reflex targets, load cells and multi-point borehole extensometer were used to monitor ground movement and deformation in real time. Deflection monitoring placed on the cavern wall for use with total station to monitor displacement accurately. Vibration monitoring, seismographs were deployed to measure vibration from the blasting, ensuring they remain within safe limits to prevent damage to the cavern and surrounding rocks. And TAIry pump storage project, real-time monitoring, extensive use of strain gauges, MPBX, load cells, and piezometer to monitor stress changes and water pressures within the rock mass, especially due to high seismic activity. Convergence monitoring, total station survey, and laser scanning were used to track the cavern wall deformations, ensuring structural integrity through continuous monitoring and timely interventions. Blasting impact monitoring and assessment, accelerate, uh, accelerometers were installed to assess the impact of each blast and adjust future blast design accordingly. Tista 5, seismic monitoring a network of geophones and accelerometer track seismic events and their impacts on the cavern stability. Essential due to the high seismicity of the region, convergence monitoring, total station survey, and laser scanning were employed to measure the deformation of the cavern walls over the time, ensuring structural integrity. Data-driven adjustments, instrumentation data allows to real-time adjustment in excavation and blasting techniques, enhancing safety and efficiency. Long-term stability, post-construction monitoring helps ensure ongoing stability of the underground cavern, securing the operational success of these hydroelectric projects. So, future scope in India, I'll tell you about this because India is a superpower in underground construction nowadays. India has significant potential for the development of underground state due to factors listed below. Current utilization, we have so far used only 15% of India's underground space and remaining 85% is to be utilized now in next 30 to 35 years. So now government of India has understood fully well that we have to develop our underground space as early as possible. And accordingly, government is making plan through their agencies. Future development plan expansion includes underground highways and metro. All highway you will see now underground. Large storage caverns for crude oil, nuclear power, hydroelectric tunnels, water supply networks, and river training projects, defense tunnels, and high altitude regions. Government targets 3,000 kilometer of tunnel planned in next 5 years across metro, rail, hydropower, water supply, and defense sectors. Capacity building. The Tunneling Association of India, in collaboration with IITs, universities like MIT Pune and Delhi Technological University, and CBIP, is conducting training programs to create skilled manpower for large scale underground works. And advanced technology and equipment. India is equipped with range borers, range climbers, DQ500, DX700, fully automated drill rigs, tunnel boring machines with a complete backup system. More than 100 TBMs are working in India at present, and this TBMs number of TBMs will increase. And we are planning to uh, manufacture TBMs in India, and there will be a tunneling center, excellence center in the coming days, you will see. Now I'll come to the safety measures. I'll discuss very basic safety, which becomes, if we don't follow this, it becomes critical. So key HSC measures for hydro tunnel projects, dedicated HSC team, ensure compliance with safety protocols, awareness programs, focus on PPEs, hazard mitigation, fire safety and emergency response, visitors induction, mandatory for safety briefing for site access, activity specific measures, strict safety protocol for the excavation, reinforcement, crane operation, and concreting. Blasting safety, monitored operation, debris clearance, and strict explosive handling. Personal protective equipment compliance, mandatory for all, especially at heights. Medical support on site, first aid, ambulances, and hospital coordination. And these are the personal protective equipments which need to be there at every ongoing project. So, personal safety outfits, and you have to be, if you are traveling inside the tunnel, you have to wear all these things. Otherwise, you will not be allowed to enter inside. That way, we are proceeding in our projects. And it has been made mandatory because our safety team is taking care of this. So, tunnel ventilation is very important because nowadays we are using the forced ventilation system. So, properly, we are designing the ventilation system. And fresh air is to be forced inside through the jet fans. Sufficient ventilation, test and measure regular intervals. Avoid recirculation from the portal, and fresh air extended close to the working phase. Avoid kinks. Repair and damage the duct immediately. So there should be a separate gang to repair the duct in case anything due to movement of vehicle. If any damage took place, it has to be uh, rectified immediately. And this ventilation is very important. So for the safety and health of the working crews inside the tunnel. So we have to design the ventilation system in such a manner uh, that how many engines are working inside at face, how many people will be there. In India, the labor is very cheap, so you will find 15 to 20 people at face at a time. But in European countries and outside world, you will find only three people, very skilled people at face, and that will take some time, but that time will come where we'll use this skilled manpower at face. That way, we are training our people. The tunnel lighting is very important because tunnel lighting are required. We have to provide extra lighting And we have to light all the places for work and access ways. Install special lighting at dangerous places. Use uh, flashing warning lights adjacent to the dangerous location. All light fittings should be protected against the ingress of water. Check, maintain, and clean lighting installation regularly. Safety lighting systems, emergency lighting, that is very important. And then we have to use the male and female coupling even if water ingress is there. So everybody is safe. There should not be any current flowing inside and then uh, to avoid that hue and cry. So electrical installation and supply lines. So here I want to tell you because this it has to be maintained in this similar manner, the way it is shown here in the picture. And all service lines should be at one side. You cannot keep three lines at one place and the other two line on the right side and left side. It has to be at one side on left side. You have to maintain all service line at this side. That is always better and safe. And proper clamp and other things are used in the way it has shown here. In similar manner, we have to do it. It's possible. And then emergency equipment inside tunnel. Your the intercom system should work like it is shown here, same way. And first aid facilities should also be there. It has to be made mandatory for making it. So it is very important. Now I'll come to the do's and don'ts. Just see these people are walking just in front of that vehicle. Anything can take place. So right way is to make a barrier and keep a clear way for this movement of vehicle so that there should not be any accident in that and people walk out safely with fluorescent jacket and personal protective equipment. So this is the wrong way of moving in a haphazard manner. The right way, you have to make a barrier wall. You have to separate path for vehicle and pedestrians. Put locos or any movement vehicles at at the end and provide videos monitoring system to observe ahead of pin when pushing. So you can adopt this way. This is the wrong way of movement and this is the right way on right side. See, it's very common practice I have seen in some of the tunnels where people are very casual about the safety because a lot of accidents are taking place because of this. People are moving in the bucket, and if there is no safety inspector available there, then people used to take this liberty. But this is not the right way, and we have to go in a manner. We have to provide a vehicle for the movement of people, and the loader and other equipment should move in the manner it is shown in the right way. These are the scaling operations. You cannot do it uh, in a casual manner. It will fall on your head. So we have to use the machine and do the scaling properly so that there should not be any loose boulder on top at ground. So this is not the way of doing the uh, drilling and this making the connections. And the on right side, this is the right way. We have to do the right wet drilling for this and always ensure this. See, we cannot do the blasting without any protection and the blasting splinters, they will come out. So few chambers and this type of containers we can use safely so that there should not be any damage. This boulder should not hit anybody working there, and safely we can execute the blasting operation. This is the wrong way. You are on a bucket of loader. We are installing the uh, wire mesh. This is not the correct way. People are using the shortcuts and then a lot of accidents are taking place. This is the right way. You should use the Manitow or the central bucket of the boomer for doing it. The other one also the wrong way, and the right way is use the boomer bucket. Here also you are installing the rock boards. This is the wrong way of doing it, and the right way you have to use the central bucket and use it properly and then do the bolting. And then people are using the debris, just standing on the debris and doing the shortcutting. That is not the correct way. And we can use the center bucket and do it properly with holding the pipes. But nowadays we are using the robo arms, so this problem is minimized. Sophisticated equipments and very reliable equipments are available in India now. So this is the wrong way of doing it, and you are straightening the wire mesh while the vehicle is passing through. Any boulder can hit you. So this is the right way of doing. We have to make a barrier wall here and then do it. The turning in tunnels, lot of accidents are taking place because of the casual approach and turning without the horns and other things. And we have to make the proper lighting here, and fluorescent jacket should be provided so that one can see. But you should not come in the hit area of the vehicle and take proper precautions. And back horn should be there so that there should not be any accident in this. The reversing in tunnel, that is very dangerous. If you are coming in the hit area, then anything can happen. So we have to make a wall. We have to make a separate path for movement of the pedestrians so that there should not be any accident. Safety is nothing but awareness. If we can create awareness by safety talks and other things, so this can be this we can make the site as a zero accident site. If we small things are there, if we use this properly dedicated in a dedicated manner, then there will not be any accident. The other one, installing the reinforcement in the tunnel, is the wrong way because we have made a temporary arrangement. It can, the person who is installing it can fall down. This is the right way of doing it, where we can lock it here and one can do it properly. This is the tunneling formwork. This is the wrong way of making the ladders here, and the right way is shown on the right side. So we have to use this and take precautions on this because every tunnel engineer has to uh, see this inside tunnel, who is working inside tunnel. He has to come across in this situation. Working in the tunnel formwork. So this is the wrong way of doing it. The person is standing here, anything can happen. This turnbuckles are there, and this is the right way of doing it, cleaning it properly. And shutter vibrators and other things should be maintained. Workplace in good order. Wear hearing protection and pouring concrete. And this is the first aid. These vehicles should be available at one call. All these things should be around nearby your site so that immediate rescue operation can be taken place, can be started. So we have to do the rescue chain, and we should know what is to be done in case of anything, if any fall of that rib or anything. So you have to call emergency uh, near that station which I showed you in the first slide. This is the other way of doing it. You have to remove it, and then in a stretcher we have to keep the person who got hit by this, and then ambulance, to call the ambulance to take you to the hospital or nearby first aid center. And this manual drilling, if you are doing, then with leg pusher and jackhammer, so you have to keep the stable condition as shown in the right side. So we have to follow this rather than following the wrong practice. And the other one, simultaneously, while drilling, we should not do the installation of rock bolts or charging the holes simultaneously with drilling. Anything can happen, and blast can take place with a slight mistake. We can face a lot of severity here. So the right side is shown the right way of loading the tunnel face, and we should follow this. Thank you very much for your attention and your patience.
Thank
Lucy?
you, sir. Yes,
Yeah.
sir. Sir, we have some questions. I'll
Yeah.
just ask you.
Yeah, please.
So, first question is from um Manoj, sir. So he's
Okay.
asking for the TAIry PSP project. Is
Yeah.
real-time monitoring being conducted for all installed geotechnical instruments such as MPBX, that is the multiple borehole extensometer,
Mm.
pressure cells and stress cells, etc., or the monitoring carried out manually?
See, we have not done it manually. With the total station, our person used to take the reading, and we have kept AML, the specialized agency there, their representative, their engineer was there, who used to do the interpretation. And every week we used to take the data, and next week the all readings are available, so that if any change is required in the design, so we can do it simultaneously as we are progressing ahead of for this excavation work. So it helped us in butterfly wall chamber and penstock assembly chamber, because people used to say before excavating those chambers that you can't do anything here because geology is so bad, you cannot make a cavern here. And rerouting was not possible. So we applied all the instruments there, and we have taken periodic reading. And design team was sitting at site from TSDC side. SMAC was the designer for our TAIry project, and they did splendid work for this project. And we didn't face any problem, and we could mitigate, because earlier, in the opinion of uh, the experts from TSDC, they used to say this project is, we can't make it, because 40 years they took commissioning in first project, but in second project also they could commission in some 7 8 years. But here they were telling it is not possible to make these caverns because geology is very bad. The investigation they have done earlier, but with these instruments they really help us a lot, and finally we could succeed, and we faced the challenge, so we have a solution for that.
Thank you, sir. Sir, another question from Manoj, sir. He's asking during Testify project, what was the technique used for geological assessment ahead of the tunnel phase, especially during
So,
tunneling? And is there any pre-consolidating grouting provision at that time?
yeah, actually it was in the we could come. we have completed this project in 2007. We could commission this project. It was a 17.69 kilometer long tunnel, and I was with Gammon India that time, and Jayaprakash was also doing it. So these instruments were not very popular, but some of the agency like Cardiorite and some geosynthesis and all other people, they were just starting their business that time. Okay, and it was not common, but tape extensometer and all these things were used because wherever cavity we have seen, there was hill was type of material and perennial source, lot of water seepage was there. We faced lot of problem. We tried everything there. Pre-grouting, we used to do make the probe drilling up to 50 meter. Then we used to assess the data. After taking out then our geologist used to do the mapping and whatever was possible that time, what was available in the market that time, we have used those things. And finally, that time pipe roofing was not very common. We brought Bhumi Construction for this from Singapore. They used MG10 pump, high pressure pump, grout pump, and one machine they brought for this. That time it was not Boomer were not that uh, very well equipped with this pipe roofing techniques. But seamless pipe we brought for this, and some of the cavity we used it successfully. But grouting was very effective. We could channelize the water from, suppose it is flowing from 10 to 12 areas, we could channelize in one area after doing the high pressure grouting. 10 bar pressure, up to 10 bar pressure, we have used the grouting. And somewhere we have used the dry motors also in ground. And finally, we restored it.
Thank you, sir. Manoj sir, do you have any more
Thank you, sir.
question?
Yeah. No, no, got it. Thank you, sir. Thank you so much.
Okay, you are
Sir, we
welcome.
sir, we have another question from Mr. Rup Kishore. He has
Yeah,
actually two doubts. He's
yep.
asking that in Vishnugad Pipalkoti he's saying that he's addressing its most challenging project. Can you please discuss about the fragmentation control by TBM team during excavation in shear or fracture zone?
No, see, I'll tell you one thing. We should not play with the alignment of the project. Okay. If you do a silly mistake, then you will land in such a great trouble, nobody can take you out. Same thing has happened there because there was a place called Heart Village. They have given the compensation to the 75% of the villagers. They have taken 75% of the compensation and they have to vacate the area so that after using the TBM, the mug should be uh, parked there after excavating. So that village could not be vacated because villagers, after taking 75% this compensation, they have not taken the balance 25%. So it got delayed. To start the project early and start the TBM early, so uh, the department changed the alignment, original alignment. They brought it somewhere 200 meter away from that place. But rock was not exposed there. It was a riverbed area in the past. RBMs was available there. And we never anticipated that boulders will be more than 1 cubic meter of size we will encounter. After going ahead 7 to 10 meter, suddenly our uh, pipe roofing got collapsed and our TBM got stuck up. It is more than 1.5 year. We were just rectifying this. Then finally, additional bypass edit and this one edit, two edits we made just to reach the front of this TBM. And then after 200 meter, we have done the NATM and we made it like a cavern, this 200-meter area. Luckily, from the surface area, when we made an edit to reach the front at 135-meter chainage, we were at 55 where TBM got stuck up. But from the another edit, we made a bypass tunnel and we reached at 135 chainage, we got the rock. And then we removed the muck manually, this conventional drill and blast method, and then push the TBM to that 135 chainage. And then there is no looking back. Finally, we succeeded in this, and TBM is working very nicely now. It is doing more than 550 meter in a month. And in 1 month, they crossed 600 meter also. That is an achievement. People were saying that in Himalayan geology, TBM are not successful, but we made it successful. But only thing, our 1.5 year precious year we lost.
So just a continuation of the question.
Yeah.
Mr. Kishore is also asking, in the same TBM tunnel, what type of instrumentation was adopted for monitoring and how the response team worked on these issues?
See everything because it's a very everything was installed in the TBM. All monitoring system we adopted. Whatever this TerraTech TBM, double seal TBM we have used, and there was a skilled team of Sally which were present. We have hired experts for this, and they were doing all operation properly, including this instrumentation, and it is successfully moving, and there is no deviation in the alignment, and there is no challenge we faced after this. This situation also developed because of the change of the alignment. Otherwise, everywhere in the dam side also, in desilting chamber, everywhere uh, it was possible to move ahead. And we have done the proper, still they are doing the proper instrumentation, taking the reading and then doing the proper um, this interpretation and accordingly moving ahead. So there is no challenge because competent niches are there, competent rock is there in dam area, Helang area. It's a good rock. But at powerhouse, at some location, in 200-meter patch was the worst. Now it is moving very well. There is no collapse. There is no any cavity. So we have not seen in 9 kilometer area any such problem. Initially, it was a problem because of the change of alignment.
Thank you, sir. Sir, we have more questions. Are you available or we can email it to you or
You can,
something?
yeah, you better do that. You can take one or two question. Uh, I am available,
Okay.
but you can send it across. I'll reply to you, and you can just send it to the concerned person.
Okay, sir. So we'll just take two questions.
Yeah,
So
go.
the question is from C. Chandrasekhar. He's asking
Okay.
what are the geophysical methods that are used to assess the subsurface strata before the tunnel, during the tunnel, and after the tunneling work completed to cross-check the voids in subsurface?
See, as such, I am not aware of the any geophysical data, but initially During DPR preparation and initial investigation, they have used all sorts of equipment, even this geophysical also. But as and when required, they used to call at Tiri. I remember they brought it because some cracks were developing. That time they brought the agency in, and then they have done the geophysical investigations. But initially, they must have done it, but it's not in my knowledge. During my tenure there at site, I have not seen any such uh, method they used during construction. Initially, during DPR preparation, they must have done it because they were open to do anything, and lot of investigation were done, and perfect DPR they prepared for this.
Okay, sir. And I think this is the last question we'll take. Ms. Manisha Yadav, she's asking, are there any codes or criteria that define safety limits for vibration, seismic loading based on seismic monitoring data, especially for tunnels, or are there any general provisions, Indian or international?
See, blast monitoring agencies are available, and we used to hire those agencies on monthly basis. They used to give their report, and they have done the instrument. They placed the instrument, and they were doing it in each and every all three projects. I have seen this blast monitoring outsourced by our company on the advice of clients, and they used to give the details because surrounding structures were also there. So we have to take this, and this is very important. So you have to design your blasting pattern accordingly as per the requirement. If rock class is not very favorable, then you have to optimize your design. That way we have outsourced the agency, a government agency, and accordingly we proceeded with their advice. It is always better to hire an agency. There's so many agencies are available, even government side, uh, these agencies are available.
Thank you, sir. And we really apologize to other people. We were not able to address your questions, but you can reach out to us over LinkedIn along with your email. We'll send it to Dr. Khali, and once we have his response, we'll share it with you. And Sir, I think this was one of the most like the longest webinar we had till now, more engaging webinar. And I would like to thank you for a wonderful webinar and this wonderful case studies. Case studies as well as the tunnel safety you touched upon. It was really advanced. It was ranging from advanced to beginner level as well. And I would like to inform all the participants and attendees that we have all our webinars on YouTube. You can access them. And this webinar with necessary permissions will be uploaded soon. And I would also like to invite the non-members to be a part of TAIym, which is solely focusing on bridging the experience of professional working professionals to the people who are new to this profession. I'm a okay. Sorry, sir.
No.
So we would like you to join our organization TAIym and be a part of such a big organization. And thank you once again, Dr. Khali, for sharing your experience. And
Thank you,
have a
Rusi.
great week
Thank,
ahead. And stay safe, sir.
thank you, Rusi, and all the participants. I'm thankful to you. So having a patient listening. And if anything in your mind, if you want to ask me anything, you can approach Rusi, and then I'll address those issues. Anytime, any other problem also you can discuss with me as and when required. And I really appreciate the efforts of young tunnelers, our young group, TAIym, and I wish you all the best. Keep doing good work and include more participants and reach out to everybody. Those who are in tunneling business, make it popular because future of tunneling lies with India, and India is the superpower in tunneling. Okay. Wish you all the best and good luck.
Thank you, sir, very much.
Okay, thank you.
Okay, okay. Bye, sir.
Bye.